Conversation is going to steer towards momentum. So, momentum is a word that we talk about a lot. You hear it in sports a lot about the momentum shift of a game. And when you think of like when they talk about in sports, how does the momentum shift? It's like who's winning, it's like that direction of who's got the advantage. Momentum in the physics world is very similar. We talk about an object that has a lot of momentum, like I know he's retired, but Rob Gronkowski was a great tight end because he had a lot of momentum when he would start to run. He was a big guy who could run very fast. And as it was such, it was very difficult to stop him. So he had a lot of momentum when he ran on the playing field in football. So objects that are moving have momentum. And momentum depends on how big you are as well as how fast you are. So momentum is like, can be thought of as inertia in motion. Okay, so as we know, it's harder to stop a large truck than a smaller truck. Just like Rob Gronkowski is a lot harder to stop than, say, oh, I don't know, the field goal kicker. He might be a little more easy to stop. So again, this idea of inertia in motion. So the concept of momentum, it depends on two things: mass times velocity, or if we don't care about direction, it's just mass times speed. So momentum is just m times v. Easy equation, don't need to memorize it, it's all good. Okay, we talked a lot about momentum. A moving truck has more momentum than a car that moves at the same speed because it's, again, mass times velocity. A fast car could have more momentum than a slow truck. It kind of depends on both of those things. And that's the idea that we want to get to, and we don't need to do that. Okay, and then a truck that's at rest has no momentum at all. It is not moving. So in order to have momentum, you need to have motion. So I wanted to also address all this fancy equation stuff that went on in the video. And I think someone had this question about this symbol right here. They thought it was a U. It's not a U. It's just the way he makes a V. So this is the introduction background information. We remember that acceleration is change in velocity of the change in time. We also know Newton's second law, that acceleration is the net force divided by the mass. And you do not need to know how to do this derivation. It's just showing you where these equations come from. And basically all the author did was set these two equal to each other because they're both an expression for A. So he put them down. And then he multiplied both sides by that delta t just to get it all on the same level. So we see something that is a direct consequence of Newton's second law and the definition of acceleration. We see this force times time. This is a time interval, and you can kind of not really look at that delta there because it's just how much time it takes, is equal to this change in m times v. So if we remember that m times v is momentum, if I exert a force and I apply that force for a certain amount of time, I can change the momentum of an object. So what did we just study that is very similar to this that also depends on speed? Well, that's kinetic energy, right? Kinetic energy kind of looks like that, has an extra 1/2 and a v squared. But we looked at how kinetic energy was changing when we exerted forces to push them and make them speed up. It's just another way to look at change in motion. So looking at the next slide, okay? The change in momentum depends on the force that acts and the length of time over which it acts. So how much is that contact time? That's important. So making a connection to what we just learned before, it's just like the change in kinetic energy. We talked about the work done to change the kinetic energy. And if we remember the formula for work, it was force exerted times a distance. So impulse is very similar looking to this concept of work, and the end result is the same. We're changing the speed of an object. So it's all connected, it all looks very similar, and this is why momentum is kind of our end of the year discussion. All right, so there we go, just kind of a connection. So we've seen this before. Again, we could think about this if we knew the force and the distance that it acted, we would say, okay, work was done to increase the kinetic energy. Or we could think about it as this force being exerted and how much time he took to push the car. And then we could look at the change in momentum. Same idea, we're looking at that change in speed. And this impulse, the impulse is force times time. It's not just force, it's force times time. just like work is force times distance. It's not a force, it's force times distance. So we just want to kind of remember that idea, that impulse isn't force, but it's related to that force. All right, so again, just looking at the formula. Again, you don't have to memorize these things. I'm going to write them all down. So the bigger the impulse you have, the bigger the change in the momentum. The more force you exert over a time, the more the object's going to speed up. And I hope that that's kind of common sense. All right, next one. So we look at two cases, increasing momentum. So increasing momentum, I'm a golfer. I love to hit golf balls. So if we want to increase the momentum of an object, we want to apply the greatest force possible for the longest time possible. And you can see here, see how this ball is being compressed here? That's extending that contact time so that we talk about compressions of golf balls. To get that golf ball to come off the face of the club really fast so that it goes really far, I really want to not only swing hard, but also have the biggest contact time. You see the same thing in hockey when players will take a slap shot. They'll bend their stick. They'll hit the ice behind the puck, so that it bends the stick so that it whips at the puck there and actually increases that contact time on the ice hockey puck. All right. Decreasing momentum. This is what we're going to spend our most of the time for the rest of the year. I know we only have 3 classes, but decreasing momentum. And this is one of the big ideas from the idea. So this is very relevant to your lives as you become new drivers very soon. And car crashes are an unfortunate reality of what happens. But that idea that if you're driving at a certain speed and you come to a sudden stop, your momentum is changing. You're going from something to nothing. And the big idea here is to help you to survive. How are cars designed to help you survive? So physics is going to help us understand why hitting a soft object is entirely different from hitting a hard object. And I know that seems very obvious, but we want to understand the reasoning behind it. So your car stops, okay? That change in momentum is the same. You go from something to nothing. You have no control over that. But what you do want to control is how much force gets exerted. So if I hit a haystack, it's going to take me, I have a big speed and my car mass, it's going to take a long time to come to a stop. So if something takes a long time to come to the stop, in order for these sides of the equations to be equal to each other, that means the force is going to be way smaller. And that's the part that improves our survival. So now if I hit a brick wall, I have the same mass, same big speed. I'm still going to have the same change in momentum. I go from something to nothing. But if I hit a brick wall, I'm going to stop in no time at all. And that means the force must be really big. So when I look at multiplying these two numbers together, they have to equal this change in momentum, which is going from something to 0. And that is the big idea that's going to carry us through the rest of the unit. So kind of coming up to the end, this is like a big idea, and this is what students get confused with. They think that hitting a haystack means less impulse. It's the same impulse, the same change in momentum, whether you hit a haystack or whether you hit a brick wall. You're going from moving really fast to stopping. What you want to change is how much time it takes for you to stop. So the bigger the time, the smaller the force. And the force is all about the survival. All right, so last time, when you extend the time, you reduce the force. So things in the car that are going to help: padded dashboard, airbags, and then to catch a moving ball, extend your hand forward and move it backward when making contact with the ball. Give with the ball so that you can extend that time, so that you have a smaller force when it hits your hand. So all of these things, you do them in everyday life. When you jump down to the ground, you're going to bend your knees. Have you ever tried to jump with stiff legs? It's going to hurt a little bit. So you bend, you give with it, you extend that collision time so that the force is less. And then these are some other examples of wrestlers. Again, you want to kind of give with it, you want to roll with it. Same idea with a boxer. If he wants to not feel the pain of that punch so much, he wants to give with that punch as opposed to leaning into the punch, then it's going to hurt. And the author explains that example too in the video. All right. So if you drop a dish on the floor, is the impulse going to be less if it lands on a carpet or if it lands on a hard floor? So lots of students immediately, misconceptions, say, oh, less impulse if it lands on carpet. But that's not the question. There's less force if it lands on the carpet. The impulse is still going to be the same, whether it hits the ground, the hard ground, the tile floor, or the carpet. The impulse is the same. It goes from some speed to nothing. The change in momentum is equal to the impulse. What we want to decrease is the force. So the dish is going to have less force when it hits the carpet, but the same change in momentum and the same impulse. So this is probably the most difficult thing that students struggle with quite a bit. And this is what we're going to kind of work on for the rest of the unit, kind of making sure we understand the difference between impulse and force. So one last think question. So if a boxer was able to make contact time 5 times longer by riding with the punch or giving with the punch, how much will the force of the impact be reduced? So again, if it's 5 times longer, that means the force is going to be 5 times less. So we have all that stuff, impulse, change, momentum, and we'll finish there. All right, good deal.